Hello, good afternoon, everyone. Could you please press the thumbs up sign if you can hear me and can hear me clearly? Okay, so thank you very much, folks. So good afternoon, everyone, and welcome to the fourth webinar of the IMath Webinar series for this semester. So let me first remind everyone that this Zoom meeting is being recorded and is being streamed live via YouTube. The link will be posted on the official Facebook page of the Institute. Okay. So let us start the webinar for this afternoon. Our speaker for today is Dr. Jade Ventura of the group's Geometry and Representations Academic Group of the Institute. He recently completed his PhD from Université de Bretagne Occidentale in France. So his talk is titled Einstein Form Metrics from Biconformal Deformations. So this is a joint work with Dr. Paul Baird. So let us all welcome Dr. Jade Ventura.
Good afternoon, everyone. I'll just share my screen. Sir, I can't share my screen.
Yes, you should be able to share now. Sorry about that.
Okay, it's okay. It's okay now.
Thank you.
Okay. So again, good afternoon. Good afternoon, everyone. I'm Jade, and today I'm presenting a portion of my doctoral dissertation, in particular the Riemannian portion of the said work. So here, when we mention Einstein metric, we mean Riemannian Einstein metric and Einstein manifold, Riemannian Einstein manifold. And we are working in dimension 4. This afternoon, I'm going to introduce to you the process of biconformal deformation and how it can be used to discover new Einstein metrics. So the main parts of this work are the parts 3, 4, 5 of the current slide. And then, but before going to the main portions, we give some preliminaries in part 2. The goal of this work is simply stated to construct Einstein metrics by way of biconformal deformation. So biconformal deformation is one of the tools of this work, along with first bullet, semiconformal maps, and the associated conformal foliations. Semiconformal maps and biconformal deformation, the two main tools we will define in later slides. So this is the outline of this work, corresponding to parts 3, 4, and 5 of the table of contents that I showed you earlier. So the first stage is, given a Riemannian manifold M, G, we compute the Ricci curvature of this manifold. And this manifold is endowed with a two-dimensional conformal foliation coming from a semiconformal subversion. And this computation in particular, we do in terms of quantities associated to the semiconformal subversion. The second stage is to compute the difference of Ricci curvatures. So we have an initial metric, G0, and then we biconformally deform it to obtain a new metric, G1. So with G0 associated with it is Rich0, and then associated with G1 is Rich1, and then in this stage we simply compute the difference Rich1 minus Rich0. And finally, stage 3, given what we know about the difference rich 1 minus rich naught, we now can start from a known Einstein metric G naught, and then biconformally deform G naught to construct new Einstein metrics G1. So that is the outline of this work. We start with some preliminaries. Here is the setup. We have a 4-dimensional oriented Riemannian manifold, that is M, comma G is the metric. We have N, comma H, an oriented Riemannian surface, that is a 2-dimensional manifold. And the bridge between these two is phi. It's a semi-conformal submersion with dilation lambda. So this dilation lambda is a smooth positive valued function from M. So what does this mean? So at each point of the manifold, at each x in M, there is associated with it a differential map, this d phi sub x. This differential map goes from the tangent vectors at x on M, the domain M, and the map goes to the tangent vectors at the image phi of x of the manifold N. So this differential map, d phi sub x, has rank 2 and nullity 2. So nullity 2 means that the kernel of this map, which we denote by v sub x, has dimension 2. We call that the vertical space. And then the orthogonal complement of that, which we denote as h sub x, we call the horizontal space. So we have this decomposition of the tangent space at x as a sum of the vertical space and the horizontal space. The semi-conformal submersion condition means that G is equal to that expression where, so this one here, phi star h. So h is the metric on the target manifold. Phi star h is the pullback of that metric. So the pullback of that metric lives on M. G on the left side lives on M. So this equation makes sense. And they're proportional by a constant of lambda negative 2, lambda being the dilation. And that equation works for the horizontal spaces only, not for the vertical spaces. Oops, I'm sorry. Okay. So the computation of the Ricci curvature is done in terms of geometric quantities related to the semi-conformal submersion phi. These geometric quantities are the dilation, the first fundamental forms of the horizontal and vertical distributions. So how do we get those? We simply restrict the metric G to horizontal vectors and to vertical vectors. So we obtain GH and GB. Those are the first fundamental forms, horizontally and vertically, respectively. Also, the second fundamental forms of the horizontal and vertical distributions, those are A and B, respectively, and their adjoints, A star and B star, respectively. Let's take a closer look at this second fundamental forms. For example, this B, second fundamental form of the vertical distribution, that simply is, you can think of that as the indication of how the vertical fibers of the map are curved inside the manifold M. Their extrinsic geometry inside the manifold M. And for B, it takes two vectors as inputs, X and Y. So what we do is take the vertical part of X and then take the vertical part of Y and then differentiate. So this nabla here is the Vivis-Civita connection. Differentiate that in the direction of dx, and whatever the derivative is, that's a vector. We take the horizontal part of that derivative. So that's B. And B star, how did we get that? B star is simply such that, let me use another color, such that G, say Z, B, X, Y. So the usual adjoint expression that you see, B star Z, X, Y. So that is how that expression for B star is obtained. So that's B and B star. For A and A star, we just simply mimic the expressions for B and B star. Continuing with the geometric quantities, we also have the intrinsic sectional curvature of the fibers of phi, Kc. The mean curvature vertically, that is 1/2 the trace of B, we denote that by mu. The mean curvature horizontally, we denote that by nu. And it turns out, using a later computation, that this mean curvature nu is related to the dilation lambda, And how are they related? So you simply take the ln of lambda and then take the gradient of the ln of lambda, that's the vector, and then take the vertical part of that vector that turns out to be equal to the mean curvature mu. And for computational purposes, we set mu perp to be the horizontal part of that vector. And finally, to top this list, the integrability one form zeta of the horizontal distribution. So we note here that the vertical distribution, so these are the fibers of phi, they are always, the vertical distribution is always integrable since these fibers are submanifolds. However, the horizontal distribution, for example, like that, with self-intersections, is not always integrable. And this integrability one form indicates whether the horizontal distribution is integrable or not. If the horizontal distribution is integrable, the integrability one form zeta is 0. That's an if and only if statement. We also use as our as an important tool in the computation orthonormal frame fields. So F here is a positive orthonormal frame field of N, E is a positive orthonormal frame field on M, such that these two conditions are satisfied. So the first two E's are horizontal vector fields, and the second two E's, the third and the fourth, are vertical vector fields. So the third and the fourth, being vertical, they are mapped by d phi. They are mapped by d phi to 0, being vertical. The first and the second, they are mapped by condition. They are mapped by d phi to lambda fi's. And we also need, for our computation, the connection one forms associated to the orthonormal frame fields defined in this slide. As mentioned, that our convention on indices is that whenever we see A, B, C, those are indices in set 1, 2, 3, 4, IJK in 1, 2, and PQR in 3, 4. We will also be needing this tensor field J, defined as follows. So E1 gets sent to E2, E2 gets sent to minus E1, E3 gets sent to E4, and E4 gets sent to minus E3. Epsilon there is just equal to +1. So E4 gets sent to minus E3. J is actually an almost complex structure on the horizontal, on individual horizontal spaces, and J is also an almost complex structure on individual vertical spaces. So it's a rotation by an angle of plus pi over 2. All in all, J is a Hermitian form on the manifold M. So for the computation of the Ricci curvature, so the Ricci curvature, oops. Better to erase that, sorry. So the Ricci curvature is defined in terms of the Riemannian curvature, and the Riemannian curvature by definition uses the Levi-Civita connection. So the Ricci curvature uses the Levi-Civita connection, and the Levi-Civita connection is completely determined by these Christoffel symbols. So if we want to compute the Ricci curvature in terms of the definition, in terms of Levi-Civita connection, we must compute these Christoffel symbols, and these are computed as follows. By the way, the numbers in my propositions, theorems, corollaries, examples are the numbers in my thesis, just to help me record things and keep track of things. So these are the Christoffel symbols that will be used in the definition of the Riemannian curvature, which in turn will be used in the definition of the Ricci curvature. You can see here in the slide that the Christoffel symbols are indeed expressed in terms of the geometric quantities, the list I showed a while ago, the geometric quantities of associated to the semi-conformal submersion field. Let's talk a bit about the second fundamental forms, A and B. Now, the second fundamental form, A, turns out can be expressed in terms of the other quantities in that list. So that takes care of A. For B, well, it's just B. But we note that useful in the computations are the divergences of B. In particular, the divergences of this tensor field B1. B1 and B are just equivalent tensors, metrically equivalent tensors. That is, they contain the same information. Now, for the divergences, since we have 3 slots for B, so this slot for X and this slot for Y and this slot for Z, we should have by definition 3 divergences. It turns out that the divergence with respect to the second slot is equal to the divergence the divergence associated with the third slot. So we just have 2, divergence 1 of B1 and divergence 2 of B2. And they are as shown here in these lemmas. So the important takeaway here is that there are these new quantities, C and C star. This is the first time that we have encountered them. So what are C and C star? So they are simply defined as follows. So they're defined in terms of traces. So explicitly, let me show you how they operate. So C has two inputs, two vector inputs, so X and Y. That's equal to, so we have G here, and that, and then let me write B star, B, and then you see those two bullets? Those two bullets are where we insert X and Y. And then trace in terms of star, that trace substar there means that we get the trace. So sum as A goes from 1 to 4, B star sub EA, this orthonormal frame field vector, of B sub EA. So let's just check that this makes sense. So B outputs a vector, so that black thing there is a vector. So this is a vector, and G of a vector comma a vector, that's a scalar. So this whole thing is a scalar, that's C. And by the way, so corollary 10.9 in my work, this C, which I defined in the work, has a geometric interpretation, namely the trace of C, which is equal also to the trace of C star, measures how close the fibers are to being totally geodesic. So for the computation of the Ricci curvature, the first main part of the work, we simply note that the Ricci curvature is decomposed into three addends: the horizontal part, which H, the vertical part, which V, and the mixed part, which mixed. And we obtain those just by restricting the inputs, the horizontal to vertical parts, in the appropriate expressions. So here I quickly outline a sample computation. For example, the horizontal part, by definition. So here, as I told you before, the Ricci curvature is defined in terms of the Riemannian curvature. And then this supersum here is a sum of two terms, which I denote by K E1 E2 GH and IPPJ. This K E1 E2 is actually just the sectional curvature of the horizontal distribution. So we compute those two individually. So the KE1 E2 part can be computed this way. This is an abridged version of the computation. You don't need to really read into these computations. We just notice a few things. For example, here in this portion, in this equation, we just use the product rule. That's why we have that. And this, how did we get this? Well, we note that this part above is a Christoffel symbol, and by the Christoffel symbol result a while ago, we can write this as this, And what other tricks do we use here? For example, this one we express in terms of its horizontal and its vertical parts. So that's why horizontality and verticality are important. Okay, so those three terms we add up. So 1, 2, 3. The first line turns out to be just the sectional curvature of n times lambda squared. The second line turns out to be the divergence of mu perp plus this term. And the third line, well, we just copy paste the third line. So that's the first addend, the KE1, E2 bit. The second addend, the IPPJ bit is also a sum of three terms, 1, 2, and 3. You'll not get into those specific lines, but it's a sum of three terms. If we use the definition, the original definition, overall, we get this 4 lines for the horizontal part of the Ricci curvature, and then we simplify it to get this first box, lemma 11.1, that's the horizontal part of the Ricci curvature. Similarly, but in a more complicated way, we can compute the vertical part of the Ricci curvature, Rich V, in the second box, and the mixed part, Rich mixed, in the third box. Adding those three boxes, we get the full Ricci curvature, horizontal plus vertical plus mixed, and getting the trace of that, we get the scalar curvature S. So now that we know how to get the Ricci curvature of a baseline manifold, we now deform that baseline manifold. So our baseline manifold is this M comma G naught, where phi is a semi-conformal submersion with dilation lambda naught, and E naught is an orthonormal frame field. We biconformally deform it, and how do we do that? We simply get the horizontal part of G naught, deform it. We also get the vertical part of G naught, deform it, and then those two deformations we add to get a G, a new metric G. That's why we have a biconformal deformation. These functions, sigma and rho, are called the deformation parameters. So this is now our new playground. M comma G, the new biconformally deformed manifold. Phi is still a semi-conformal submersion, but now it has a dilation of sigma lambda naught. And E naught is no longer a orthonormal frame field. Rather, E is an orthonormal frame field where the EIs and the EPs are defined as follows. So many functions are changed, many geometric quantities are changed. However, there are unchanged notions as we go from G naught, the original G naught, to the deformed metric G. Specifically, the notions of horizontality and verticality are unchanged, and also the almost complex structures J are unchanged. So what this means is that, so associated with our original G naught are the almost complex structures J naught. Associated with the deformed new metric G are the almost complex structures J. It turns out that these are the same. So notice that there are zero subscripts or superscripts in the earlier slide. So that's the main theme. For the old metric, we use a subscript or superscript of 0. And for the new metric, we leave the quantities unsubscripted or unsuperscripted. The goal in this part is to express the unsubscripted or unsuperscripted quantities in terms of the old ones, the ones with the subscript 0 or the superscript 0. The examples are some examples are in these boxes. So you can see here that on the left sides, you have unsubscripted, unsuperscripted quantities, and they are expressed in terms of quantities that have subscript or superscript 0, and they're also expressed in terms of the deformation parameters sigma and rho. We can compute the difference of the Libby-Civita connection as we go from the original metric to the biconformally deformed metric. An important thing to note here is that this connection lambda naught is not a tensor. The connection lambda is also not a tensor, but from this theorem, the difference of the two is a tensor. So this is the change of the Ricci curvature. So this one is for the change in the horizontal part of the Ricci curvature, the change in the vertical part of the Ricci curvature, and then the change in the mixed part of the Ricci curvature. So with these three boxes, horizontal, vertical, and mixed, we in effect have determined the change in the full Ricci curvature as we go from an original metric G naught to a biconformally deformed metric G. So that's the second main part of the work. For the third main part, we talk about Einstein metrics. In the Riemannian context, we are in the Riemannian context today. This is the Einstein equation, which equals lambda G. A metric that satisfies this equation is called an Einstein metric. And a manifold, let me annotate. So if G satisfies this equation, it's called an Einstein metric. And if G is a metric in this pair MG, where M is the topological manifold, a smooth manifold, and G is a metric on it, and G is an Einstein metric, we call this pair an Einstein manifold. So that's the Einstein equation in the Riemannian context, which we are working with today. So this is the program in this part. We start with a baseline metric, G naught, a baseline Einstein metric, so it satisfies the Einstein equation with subscripts, with 0 subscripts. So Rich naught equals lambda naught G naught. And what we want is to answer the question, when is the new metric an Einstein metric also? So G is an Einstein metric with constant of proportionality lambda. That is Rich equals lambda G, if and only if the following system holds. So how did we get that system? We subtract the first equation from the second equation, and then divvy up into the horizontal, vertical, mixed parts. And that is what we did to arrive at this system. And then some technicality, motivated by this system, we define the functions lambda AB as follows. The general theorem, the general template theorem, is shown here in this slide. The new deformed metric G is an Einstein metric if and only if the following system of 9 equations holds. Actually, this is a system of PDEs, nine partial differential equations. And in this case, the constant of proportionality lambda is equal to either sigma squared lambda II for any I, or rho squared lambda PP for any P. So using this main general template theorem as our guide, we discussed a very simple example of G naught being the usual Euclidean form metric. So here, mg naught is the usual Euclidean for space R4, and H is R2. So G naught and H are as follows. Epsilon there is just 1, since we are working in the Riemannian case. So you can see that things here are very simple because the dilation is just 1 if we set the P, the map P, to be the canonical projection onto the first 2 coordinates. The dilation is just 1 and the other geometric quantities just vanish. So this is a very simple example, but very instructive one on how to apply that template theorem that I showed you before. So as a summary, the Euclidean form metric is the sum of dx1 squared, dx2 squared, dx3 squared, and dx4 squared, whereas the new deformed metric is, so this is the horizontal part. We deform it by a factor of sigma -2. This is the vertical part. We deform it by a factor of rho -2. And those two deformations we add together to get the new metric G, the biconformally deformed metric G. So I'll just show you one example of an application. So suppose that sigma and rho are 1 parameter functions. In particular, suppose they are functions of just the first coordinate x1. So this is the example. So sigma is sigma x1 and rho is rho x1. In this case, the system of PDEs become this system of 4 partial differential equations. You can see there are 2 equations, but there are 4 in total since I runs from 1 to 2. Before I go on further, let me just fast forward a bit to the theorem that we are going to arrive at. So for now, it is not important to read what the theorem says. I'll just point out that in this theorem, in this characterization theorem, there are 5 items: 1a, 1b, 2, 3, and 4. So again, there are 1a, 1b, 2, 3, and 4. We have to remember that as we go back. Let's go back. Okay. So for this example, we further suppose that rho and sigma rho inverse are not constant functions. And this is where the items 1A, 1B, 2 come into play, because if we suppose that rho is a constant function, we get the item 1A and 1B. If we suppose that rho is not a constant function, but sigma over rho is a constant function, we get possibility 2. So those are the first 3 items in the theorem. But supposing they are not true, then we have these 2 equations. The first one is an ODE of rho, and the second one expresses sigma in terms of rho. Suppose further that D is not 0. Why? Because if we suppose that D equals 0, we get possibility number 3. So we have covered 1A, 1B, 2, and number 3. So if we suppose that D is not 0, we get this solution to the differential equation. This side here multiplied by eta, which is just plus minus 1. We denote by h of rho. And then we have the following. Rho defined by the inverse function of h, and sigma defined in terms of rho. Note again that sigma and rho are the deformation parameters. So theoretically, once we know what sigma and rho are, we know exactly what the deformation of, we know exactly how we deform the original metric genome. So plugging in, we get that the new metric G is as follows. And the new metric G satisfies this equation, which equals lambda G. That is, it's an Einstein metric where lambda is given here. Note in particular that lambda is never 0 because we have assumed that B is not 0, and then this is always positive, and then it turns out that rho is never equal to D in this case. So this is just either plus or minus 1. So this function rho here has 6 different shapes, graph shapes, and these are A, B, C, D, E, F, these shapes. We note here that in this case, in this asymptotic behavior, by the way, this is just D. This level is just D here, this horizontal asymptotes. So in letter C, as we go to negative infinity, on letter D as we go to positive infinity, letter E as we go to positive infinity, letter F as we go to positive infinity, we reach the limiting behavior D, the constant D. And if we go back, if we reach D, then this one vanishes as we reach D. So this one vanishes. And this one becomes a constant. So this constant times this is just the 2 metric, the Euclidean 2 metric, the usual R2 metric. So it's asymptotically approaching R2. So this, and this asymptotically approaches, means that the metric asymptotically approaches R2. On the other hand, this limit here, well, let me use another color. This limit here, this limit of 0 here, this also, and this means that the corresponding metrics asymptotically approach the hyperbolic 4 metric. I'll show you what that hyperbolic 4 metric is. It's something like this: x negative 2 times dx squared plus dy squared plus dz squared plus dw squared. So that's the asymptotic behavior. And in particular, for these two families, so these are the families that I described in the abstract of this talk. Namely, for these families, on one end, they asymptotically collapse to the Euclidean metric for R2, and at another end, they asymptotically collapse to the hyperbolic 4 metric, the metric written in green. So that's possibility number 4, giving us this theorem: a maximal biconformally deformed metric G, where the deformation parameter sigma and rho just depend on a parameter, one parameter, say x1, is an Einstein metric if and only if one of the following holds. So either it is Ritchie-flat or it is non-Ritchie-flat. For Ritchie-flat, it can be 1A, isometric to the Euclidean 4 metric, the metric of R4, the usual one, or it can be 1B, isometric to the product of this metrics A and B, or it can be item 3. It can be homothetic to ds squared equals that metric written there. The other possibility is that it is Ritchie-flat. So for under Ritchie-flatness, there are 2 sub-possibilities. Either number 2, G is homothetic to the hyperbolic 4 metric, the green metric that I wrote a while ago. And finally, possibility number 4, which the example gives, G is the metric given in the previous example. So this is a characterization theorem. Moreover, in item 1B, G asymptotically collapses to the usual metric of R2. In item 4, either G asymptotically collapses to the usual metric of R2 or to a metric that is homothetic to the hyperbolic 4 metric. So that's the remaining case of my work with Dr. Colbert. We have in the paper have other examples of what sigma and rho can be, but this one I think is an instructive case in the sense that it accomplishes the goal, which is to output a new Einstein metric given an old Einstein metric. And it follows the steps, the prototypical steps of our work. So that will be all for this afternoon. Thank you very much for listening.
Okay, thank you very much, Dr. Ventura. Let us all give Dr. Ventura a warm round of virtual applause. Thank you very much for that talk. Okay, so the floor is now open for questions. So does anyone have a question? So you can unmute yourself, or you can type your question in the chat box. You have questions? Okay.
Gino?
Hi, yes, sir. Good afternoon, po.
Sige, let me just first thank you, Jade, and welcome back. Congratulations on your degree. Good to see you and good to have you here in our webinar. Ang tanong ko, okay, now you can get this new Einstein metrics, no? Pero what? And I saw that some of them turn out to give you other known metrics.
The known, yes, sir. Yes, sir.
Pero why do you want a new metric? What is your interest? Does this help in the classification of Einstein manifolds? O ano ba yung status nun, yung oriented Einstein manifold?
Oh, for example, sir, yung possibility number 4 kanina, hindi namin talaga sure kung known na siya or hindi, as we don't have an encyclopedia of known Einstein manifolds. But I would say that the original motivation of this work is for the semi-Riemannian case, yung talagang space-time manifolds. And then the goal for that one is to arrive at new Einstein solutions for the Einstein equation in the space-time context. And then yun kasi, if we just assume in the Einstein equation that there are no matter fields and there are no electromagnetic fields and such, and if we assume just vacuum contribution, then we get the Einstein equation for the Riemannian context. So that's why naging pahabol din siya sa work namin. That's why we also covered it.
Okay, okay, go ahead.
Yeah. But yung nga sinabi ko kanina, sir, yung yung possibility number 4, we don't really know if may naka-discover na ba nun before us. Yeah. But it got published, so.
Kasi ang tinitignan mo, 4-dimension, is the same method applicable to higher dimension, like 8-dimension or...
That one, sir, you have to decide how to say partition, for example, 8. Kasi ang ginawa dito is horizontal plus vertical. So 2 plus 2, yung pag-partition. The 8, you can, 2 plus 6 or 4 plus 4. And preferably even, kasi nga, dito sa work na to, ginamit yung mga almost complex structure ng horizontal and vertical, for example. So parang yung E1 goes to E2, E2 goes to minus E1, yung two-dimensional rotation na yan, plus pi over 2. So I don't know how to, I'm not sure how to divvy up yung 8 dimensions pag ganun.
Okay. Si Rich Chacha yata question kanina.
Thank you.
So thank you.
I was really curious why you choose the 4-dimensional space. And by the way, congratulations muna po.
Thank you, sir.
And a very interesting presentation. Tapos, yun nga, parang nagtataka ko, bakit 4? Because ako my dissertation on differential geometry was also 4 because we know how special the 4-dimensional space in almost complex geometry. Lagi siyang special case. So, yun nga, curious din ako if we can Kahit man lang sa 6, if we can.
Yeah, true, sir. Yun nga, as I said before, it's just a parang spin-off ng interest namin sa space-time manifolds, which are 4 dimensions. But technically, there's nothing stopping us into extending to higher dimensions. Basta ma-clear lang natin kung paano i-partition yung mga dimensions.
Yeah, but if you are interested in working on space-time, this is a very good start in looking at the metric for biconformal deformation.
Yes, sir.
Okay, thank you, Sir Cha. Do we have any other question from the audience? So maybe Sir Jade, that's a good start for some future work or some ideas for future work, and
for sure.
For the students who are watching also that who may be interested in us. So yeah, that's some idea. So do we have any question else? Okay. So Sir Joe.
Dun sa theorem mo, although this applies to the particular rho and sigma, no? Pero hindi lumilitaw ba yung mga ibang metric, kunyari yung sa Kähler or yung mga kalabiyaw, yung mga sa or complex projective, parang hindi ko nakita do sa pag kunyari flat case or something or non-flat.
Anong pong metric ulit, sir, in particular?
Kunyari yung kunyari metric ng mga Kähler, hyper-Kähler manifold or Kähler manifolds.
That one we did not look at kung alin sa kanila ang other type of metrics pa.
Okay, kasi I saw the hyperbolic and what else. How about yung metric on SN, yung the usual?
Yeah, that one S4 hindi nag-appear, sir. Metric on S4.
Okay. Okay, it's interesting. Very nice.
Yeah. That napaisip ako. Ba't nga ba H4 ano ba kasi?
You mentioned ata kanina that your anong klaseng space yung kinukonsider nyo? Hermitian ba? Tama ba? Hermitian yung space.
Yeah, sir. That J1.
Oo. Na Hermitian siya dapat.
It gives a Hermitian structure.
It changes when you shift to another type of complex manifold.
Hindi ko lang alam kung ano yung tsura sa pag complex.
Oo. Medyo mas iba yung mga kwan nila. Yung lumalabas na Christoffel symbols nila.
Okay.
Okay po, so maraming salamat po ulit sa... Do we have any other question? Okay, so if there are no more questions, let us again give Dr. Jade Ventura a warm round of virtual applause. So again, congratulations on completing your PhD. Okay.
Thank you po.
And again, thank you for giving that nice talk. And thank you for the audience for your attention. Okay, so...
Magbabakasyon raw muna si Jade. Pero bigyan ka ng load yan for next sem.
Sir?
Bigyan ka na ng load.
Bigyan ng load yan.
Okay, good.
Some graduate, so maybe some graduate class also, or some introductory, some geometry course. Okay, so thank you. And so our next webinar will be 2 weeks from now. I think it will be from the coding and number theory group, if I'm not mistaken. Anyway, it will be announced on our IMath Facebook page. Okay, so thank you very much. Thank you to everyone for attending, and we will see you again on our next webinar. So enjoy the rest of the afternoon. Goodbye.
Bye.
Bye.
Bye po.
Bye. Ingat-ingat.
Durian.
Durian with the French flavor.
Oo, pupuntang Davao pero hindi raw sa Davao City sa Davao del Sur.
Punta pala sa Davao si ano.
Baka mangangampanya. ang mga ngampanya.
Masarap
Sige,
ang mga prutas doon sa area na yun.
Gino, salamat. Sino next time sa coding? Meron ng tao?
CNT po, sir. Hindi pa po, sir, na-confirm po.
Okay.